In our world today, we create a massive amount of data every single second. Think about all the photos we share, the videos we watch, and the information businesses collect. Sometimes this data becomes too big for a single computer to handle effectively. Imagine trying to fit an entire ocean into a small bucket. It simply will not work. This is where a clever idea called distributed programming comes into play. It is the technique of breaking a very large task into smaller, more manageable pieces. Then, these smaller pieces are sent out to a group of computers, often called a cluster, to be worked on at the same time. This parallel processing makes everything much faster and more efficient. This approach is like having a huge team of helpers instead of trying to do all the work by yourself. If you had to build a large house alone, it might take you years to complete it. However, if you hire a team of builders, electricians, and plumbers, they can all work on different parts of the house simultaneously. The house gets built in a fraction of the time because the work is distributed among many skilled individuals. This is the fundamental principle behind distributed computing frameworks. They manage the complex job of splitting the data, sending it to different machines, monitoring the progress, and then bringing all the results back together into one final, coherent answer. Two of the most popular and powerful tools for this kind of work are Dask and Apache Spark. Both are designed to help data scientists and engineers process huge data sets that would otherwise be impossible to manage. They are the expert team leaders who organize the work for your cluster of computers. While they both aim to achieve the same goal of enabling large-scale data processing, they do so in very different ways. Understanding their unique philosophies, their strengths, and their weaknesses is incredibly important. Choosing the right tool for your specific project can make a huge difference in performance, development time, and overall success. This comparison will help you navigate the choice between these two excellent frameworks. We will look at what makes Dask special, particularly for those who love working in Python. Then, we will explore the powerful and comprehensive ecosystem that Apache Spark offers to its users. By examining their core differences in areas like language integration, ease of use, and performance characteristics, you will gain a clearer picture of their ideal applications. The goal is to provide you with the knowledge you need to confidently select the best tool. Whether you are analyzing scientific data, building machine learning models, or managing massive business intelligence pipelines. Dask is a flexible open source library for parallel computing written purely in Python. It was created with the Python data science ecosystem firmly in mind. Imagine you are very comfortable using popular Python libraries like NumPy for numerical calculations, Pandas for data manipulation, or scikit-learn for machine learning. Dask is designed to scale these familiar tools. It mirrors their APIs, which means the code you write with Dask looks and feels almost identical to the code you already know. This makes the transition from working on a single machine to working on a distributed cluster incredibly smooth for Python developers. The magic of Dask lies in its dynamic task scheduling. When you write a Dask operation, it doesn't compute the result right away. Instead, it builds a graph of all the tasks that need to be done. Think of this as a detailed to-do list or a recipe. This lazy evaluation allows Dask to be very clever about how and when it executes your code. It can optimize the steps, minimize data movement between computers, and handle complex workflows efficiently. This flexibility makes Dask excellent for interactive computing and for tackling problems with irregular or complicated patterns, which are common in scientific research and advanced analytics. One of Dask's greatest strengths is its simplicity and lightweight nature. Setting up a Dask cluster can be as easy as running a few lines of code on your local machine, or it can be scaled up to run on thousands of nodes in a massive cloud environment. It doesn't require a dedicated resource manager like Spark often does. It can work with what you already have. This makes it very accessible for individuals, small teams, or anyone who wants to start with parallel computing without a lot of setup overhead. It integrates seamlessly into existing Python projects, allowing you to parallelize your code piece by piece as needed. Because Dask is native to Python, it excels at handling Python-specific workloads. It has no trouble managing complex Python objects or running custom functions that rely on the vast landscape of Python libraries. This is a significant advantage when your project involves more than just standard SQL-like queries. If your analysis requires intricate algorithms, specialized simulations, or interactions with other Python-based systems, Dask provides a natural and powerful environment. It empowers Python users to scale their existing skills and code bases to tackle big data challenges without ever having to leave their preferred programming ecosystem. Apache Spark is a unified analytics engine for large-scale data processing. It was developed to be a faster and more flexible successor to an earlier technology called Hadoop MapReduce. Spark's core strength is its comprehensive and integrated ecosystem. It isn't just one tool, it's a full suite of tools that work together seamlessly. This suite includes Spark SQL for working with structured data, Spark Streaming for processing real-time data streams, MMLLIB for scalable machine learning, and Graphics for graph analytics. This all-in-one approach means you can use a single framework to handle a wide variety of big data tasks, from data cleaning to model training. At the heart of Spark is a data structure called the Resilient Distributed Data Set, or RDD. An RDD is an immutable distributed collection of objects. Spark performs operations on these RDDs in parallel across the cluster. While RDDs provide low-level control, most modern Spark development uses higher-level APIs like data frames and datasets. These APIs provide a more structured view of the data, similar to a table in a database. This structure allows Spark's powerful Catalyst optimizer to analyze your queries, understand your intent, and create a highly efficient plan for executing the work across the cluster, leading to exceptional performance. Spark was originally written in a programming language called Scala, which runs on the Java virtual machine. This JVM foundation is a key part of its identity and performance. It allows Spark to be very fast and robust, benefiting from years of JVM development and optimization. While Spark has excellent APIs for other languages, including Python through a library called PySpark Java and R, its core operations are always executed on the JVM. This can sometimes create a small barrier when moving data between Python and the JVM, a process known as serialization, but it is also the source of its raw processing power. The maturity and widespread adoption of Apache Spark are among its biggest advantages. It has been a dominant force in the big data world for many years and is supported by a massive global community. This means there is a wealth of documentation, tutorials, and third-party tools available. It is a battle-tested, reliable, and highly scalable solution trusted by large enterprises for their most critical data pipelines. When you need a robust, feature-rich platform that can handle almost any data processing challenge at scale, Apache Spark stands out as an industry standard choice with a proven track record of success. When choosing between Dask and Apache Spark, the decision often comes down to your specific project needs and your team's existing skills. The most significant difference is their relationship with programming languages. Dask is Python native. It was built in Python for Python users. This tight integration means it handles complex Python code and libraries effortlessly. In contrast, Spark is built on the JVM using Scala and Java. While its Python API, PySpark, is excellent and widely used, there can be a slight overhead when converting data or running custom Python functions. If your team lives and breathes Python, Dask often provides a more natural and seamless development experience. Performance is another critical factor, though the answer to which is faster is not simple. Spark, with its sophisticated Catalyst query optimizer, often excels at complex SQL-style queries and traditional ETL pipelines on structured tabular data. Its planning phase allows it to create a highly optimized execution path. Dask, with its dynamic and flexible scheduler, can be faster for workloads with complex non-tabular logic or those that require custom algorithms common in scientific computing. Dask's lower overhead can also make it quicker for medium-sized datasets or when used on a single powerful machine. Ease of use and the surrounding ecosystem also play a major role. Dask is often considered easier to get started with, especially for those already familiar with Pandas and NumPy. Its setup can be minimal, and it integrates smoothly into existing Python scripts. Spark, being a more comprehensive all-in-one platform, can have a steeper learning curve and a more involved setup process, often requiring a cluster manager like Yarn or Kubernetes. However, Spark's mature ecosystem is a huge advantage, offering robust tools for streaming, graph processing, and machine learning that are tightly integrated and supported by a vast community. Ultimately, the best choice depends on your use case. Choose Dask when your project is heavily invested in the Python ecosystem, involves complex custom algorithms, or when you need a lightweight, flexible tool for interactive analysis and rapid prototyping. It's perfect for data scientists scaling their existing Pandas workflows. Choose Apache Spark when you need a mature, battle-tested, all-in-one platform for large-scale ETL, structured data processing, and real-time streaming. It's the industry standard for building robust, high-performance data pipelines in enterprise environments, especially where multiple languages like Scala, Java, and Python are in use.